So this is joint work with Jasper Cooper, who's a grad student at Columbia, Alex Kopeck at Yale, and McCartan Humphreys at the WSB in Berlin. And what we have been working on is a new line of attack, a different line of attack on the problems of credibility and reproducibility in social science research that focuses on improving research designs. And so the idea is that we're going to set up a set of tools that help us as researchers to select better, well-powered designs and to provide us with the tools to credibly signal to reviewers and readers about the quality of those research designs. So how do we know if a design is good now? How do we go about thinking about this problem today? There's kind of three ways that we do this in planning for studies. The first is we rely on statistical formula from our textbooks, from our statistics classes in college and grad school. The second is software tools that typically rely on those formula as well and have drop-down menus and help us focus attention on the parameters that are most important. So maybe it asks us for the sample size that we have in mind, our implied effect size, and a couple of other things. And then if we don't use one of those, if we think that one of these tools doesn't account for the kind of design that we have in mind, sort of more advanced coders might write up their design in computer code and simulate their design using its sort of full features. So I think this kind of highlights two drawbacks to these. The first is that these software tools and the set of formula are only set up for a small number of the kinds of designs that social scientists are actually using. So for example, this power calculator from EGEP has a clustered design or not clustered design, and you can choose either a binary outcome or a continuous outcome, and then you can choose your effect size and the sample size. And so any other kind of design element that you might have, for example, having blocking in your design, isn't accounted for in these tools, and so you may get the wrong answer. In our paper, we go through this kind of exercise of looking through these tools and what kinds of problems you might come into contact with. So these kind of raise the question of what do we need to know about your design in order to answer the question, is this a good design for the question that I'm trying to ask? So we've come up with a couple of examples in social sciences. So one is the consort guidelines from 2010, which is a long questionnaire that's been discussed a couple of times, where it asks you everything from how you're selecting subjects into your pool, all the way to what kind of estimator you're going to use. But I think one of the problems that this has raised is that we don't have a clear sense of what those important things should be on this checklist. And so in other domains of research, where we've tried to carry out the same exercise of developing a checklist that is complete in some sense, is that there hasn't been a convergence of what those important elements are. And so David McKenzie at the World Bank has a PAP checklist that's meant to completely describe your design before you implement it. He's identified 9 features. The consort guidelines have 22, and Alejandro Ganimian has a PAP template that has 60 elements. So what we first propose is a definition of what we think are the elements of a research design that we're going to need in order to be able to answer the question for ourselves, is this a good design for the question that I'm asking? And it has four elements. The first is a model of how the world works. This is a set of assumptions about pre-treatment variables, about how the world responds to a treatment, so your potential outcomes if you're conducting an experiment or some other kind of causal analysis, and probability distributions of the pre-treatment variables. It's basically how you imagine the world to be and how it responds to the kinds of interventions that you may carry out, both including treatments, but also your measurement. In addition to your model, we have an inquiry. An inquiry is just a question about the world. So this is your estimand. This is an average treatment effect or the average level of support for a political candidate. Then we have the two that are under researcher control, which are the data strategy. This is how you as a researcher are going to intervene in the world to learn about the model. So this includes your sampling strategy, your treatment assignment strategy, but also other things like your measurement strategy. Am I going to interview people in person, and does that matter for the potential outcomes? Finally, we have the answer strategy, and that's how I'm going to answer, how I'm going to provide an answer to my inquiry. So this is your estimator, this is your choice of a regression or difference in means, and kind of a specification of the tests that you're going to carry out. To take this model of a design, this 4-element definition of what we need to know about your design to then answer the question, is this a good design for the inquiry that I've posed? We need two more parts. The first is a diagnosand. So this is just a statistical summary of a design. So this is things like estimation bias, or the mean difference between the estimate and the true estimand. So this, this might be the power, so the average proportion of times that the p-value is less than 0.05, or sorry, I should have said 0.05. There are a range of other those are the two diagnosands that I think we often think about, but thinking about it more systematically opens up a range of other possibilities, thinking about the type S error rate, how often we get the sign wrong in our estimates, the exaggeration ratio, how large in magnitude our errors in estimating the effect are. We could also think about the value for money of the treatment. So are we going to, is this treatment worth carrying out given its cost, its robustness, the robustness of your design to different, or the robustness of your answer strategy to different possible models of the world, and on and on. So then the kind of answer that we provide to the question of how much information do we need to know and what information do we need to know in order to answer the question, is this a good research design for the inquiry you pose, is that we're not going to tell you that. And instead we're going to ask you to answer the question, can you estimate a diagnosand that you care about your design? So can you estimate the power of your design from what you know about the design, from what you've specified? And so this implies that the answer to that question is going to be different depending on the diagnosand that you're interested in. So if you're interested in the power of the design, you're going to have to write down the model of the design, including the potential outcomes. You're going to have to write down your data strategy, how you're assigning treatment, and you're going to have to write down your answer strategy. So how are you taking the data and turning it into an answer? But what you need to know in order to calculate other diagnosands, like you may be interested in imbalance. So how often in my experiment am I going to get a largely imbalanced set of covariates? There we don't need to specify the answer strategy because it's not a function of that. So it's just a function of our description of the variables and how we're going to collect data and assign treatments among them. Okay, so how do we use this then to help us choose better powered designs and to signal the quality of the design? We ask we suggest that we do two things before we go out into the world and carry out our design. The first is to declare your design. And what that means is to take these model, inquiry, data strategy, and answer strategy and write out each of them in code. And the purpose of that is that then that enables you to diagnose your design, which just means simulating the design over and over again and estimating these diagnosands from the repeated simulation of your design. So I'll show you some R code. We've written a set of R packages that help you to do all of this. We're also working on tools for Stata and for the web that I'll talk about in a minute, just to kind of illustrate and give you a flavor for how this works and what kind of information you need to be able to provide in order for our tools to help you answer the question, is this a good design for the question that you have? So first you specify your model of how the world works. So here we have a two-arm experiment that we're going to carry out. And so we have to declare, there are two parts of the model that are particularly important here. And each of these is run through an R function where we declare the features of these designs. And so we define our population as a set of 2,100 units, a small town, and the variables that we're going to, the variables that exist in the world that are relevant to our design. So we have a noise parameter. We're going to collect data on the age from 18 to 75, and then we're going to code a variable that indicates whether you're under 40 or not. We then define, secondly, the potential outcomes under this treatment. So we're going to assign a treatment to some people, and your potential outcomes under the treatment is going to be the same as under control, but you're going to have a 0.25 standard deviation treatment effect, and there's going to be an additional bump from the treatment if you are young. So you'll have an additional 0.1 treatment effect. We provide some tools that make this easy to do, but you can also use our tools to simulate your design and calculate diagnosands with your own functions. So if you've written your own R Stata functions that randomize your treatments or that analyze it, you can bring those in and just give us your function and tell us the kind of important parameters. So that's your model. Your inquiry is simple. So you declare your estimand, the question that you're asking about the world. So here we're going to have two estimands for this two-arm trial. We're interested in the average treatment effect, average difference in the potential outcomes. And we're interested, secondly, in a very common estimand, which is the difference in conditional average treatment effects. So we want to know, is this treatment more effective for people who are under 40 than it is for people who are over 40? And so we just write these out. Third, we're going to define our data strategy. And in this two-arm experiment, we have two parts of the data strategy. One is that we're going to sample units. So we define the number of units that we're going to sample, 250, and the number of units that we're going to assign to the treatment within those 250. So we'll assign 125 to treatment and 125 to control. And this is using our randomizer package, which we're releasing soon, that has a large range of kind of common randomization and sampling tools that social scientists are using that makes it easy to tell us about your design. Third, you define your answer strategy. So here, because we have two questions that we're trying to answer, we have two estimators. So the first estimator that targets the average treatment effect is just the difference in means. So we just have a difference in means estimator set up there. And we tell DeclareDesign that we are targeting the average treatment effect estimand. Secondly, we have a regression estimator that is the interaction of the treatment and this indicator for whether you're under 40. So we put that all together as the declaration of your design. And so we declare the design as each of these elements. We have a population, potential outcomes. We have these two estimands. Our sampling step, assignment step, we're going to reveal the outcomes from the potential outcomes. And then we're going to calculate these two estimators. The last thing that we need is our diagnose-ands. So this is the statistical summary of the design. And so we're going to focus on three here. The first is bias, the average difference in the estimate and the estimand, the power, and the mean, just the mean of the estimate, so we can see what it's giving back. So that's the first step, declaring your design, providing us with code for each of the steps of your design and your model of the world. And the second step is to diagnose your design, so simulating the design to estimate the diagnosands. So that works in kind of two steps. So the first is that we need to simulate a realization of the design. We need to simulate the process of running our experiment. And so we draw the population, we calculate the potential outcomes from that. We calculate these two estimands using the data drawn from the population. And then we sample from the population, assign the treatment, reveal the outcomes, and calculate the estimates from our two defined estimators. The second part of that then is that we do this some number of times, 1,000, 10,000 times, and we'll provide a standard error for the diagnosand so you can get a sense of whether the choice of that number matters. And so DeclareDesign then runs your design over and over again and calculates the diagnosands. So the first thing that you get out of that is 1,000 estimates of your answer. And so these are the sample mean estimates, and the red line is the estimand, so we can see that the estimates are centered around the estimate as we expect them to be. And then these are the confidence intervals from those draws. And so in blue are confidence intervals that cover the true estimand, and the darker blue confidence intervals are outside of it. And so as we would expect, about 5% of them are not covering the estimand. Okay, so then we get to the part that we were really looking for, which was these diagnosands. And so it takes those repeated runs of your design and then calculates these diagnosands that you've defined, or the ones that we give you by default. And so for these two different inquiries that we have about the average treatment effect and the difference in the conditional average treatment effect, we see that the mean average treatment effect is 0.29, and the difference in the conditional average treatment effects is 0.1 as we set it up. Here, importantly, we see that we didn't achieve the threshold of 0.8 for power. So this is a design that would be underpowered for studying the average treatment effect. And we see that the power of the difference in the conditional average treatment effects is extremely low. And this highlights an important feature of this setup, which is that we were able to tell the computer exactly what question we were trying to ask and exactly what we were going to do with the data, whereas most of the online tools and formula, it's difficult to have this it would be straightforward for us to figure out what the power for the average treatment effect is, and not straightforward to figure out this more complicated power to detect this more complicated heterogeneous effects analysis. Okay, so we want you to declare your design, diagnose your design, and then obviously to improve your design. And this, setting us up as an iterative process where you figure out what the values of the diagnosands are, decide whether those are sufficient for your purposes, and then improve the design if not. We provide kind of 3 ways to help with that improving your design step. They are to front load design decisions, make it easier for you to think about what the options are, to compare the properties of different data strategies and analysis strategies, and to explore the robustness of the design to different possible models. So primarily, we can help you front load your design decisions and think about what the options are, for example, for analysis, from that design that you have defined in code, drawing your data. And so it gives you just a data frame that you can start to analyze with whatever regression tools or estimators you have, and it can highlight problems that you don't anticipate, typically until you get the actual data back. And so this helps you to sort of think about what the options for your sampling and treatment assignment and particularly your analysis strategy. Secondly, we can compare different strategies to see what their properties are. And so we saw that we didn't reach the traditional cutoff of 0.8 on the power for the average treatment effect. And so maybe we want to bump up our power and compare those 2 designs. And so we can modify the design and add this potentially this alternative sampling strategy to sample more. And then this will give us back, we can diagnose those 2 designs together, and we can see that we reached the 0.8 threshold for the average treatment effect with that larger sampling size, that better well-powered design. And we see still that we have no chance of detecting this difference in the conditional average treatment effects. Finally, we can look at the robustness to other models. So we want to know, we made a set of assumptions about how variables are distributed. We made a set of assumptions about the potential outcomes, but of course those may be wrong. And so we may want to know, is this design going to provide us is this design going to be a good design under different possible models of the world? And so we can think about, for example, thinking about how the power and bias will be affected by changing the potential outcomes function. We think these tools have a lot of complementarities with the other kinds of open science tools that we've been talking about for the last couple of days. In particular, we think this is very useful for developing pre-analysis plans, registered reports, and for setting us up to be able to conduct results blind review. Because it provides a way to figure out what you need to share with readers and reviewers about your design to help them judge and help convince them that you have selected a good design for the question that you're trying to ask. And it provides for results blind review and registered reports a way to simulate data as you will actually collect it, so that you can create the tables and figures that you will later using this simulated data. We also think it's complementary with mandated data and code sharing, and we think that it adds an additional step in which we should be sharing our code, our data, and the details of our design. Finally, I think it enables a new kind of replication, which is a little different, which is complementary to the kinds of analysis, analytical replications that 3IE is funding, for example. Here, this is a design replication in which we replicate the design that they had and explore its properties under different possible models and try to judge whether we think, as the reanalyzer, this is a good design. And so it provides tools both for the original author and the new author. For the original author, this allows you to reject reanalysis strategies if you switch inquiries, which often happens when you change details of the estimators. And it allows you to reject reanalysis strategies if the change in the analysis strategy produces different results. So they provide an estimator and they show that the coefficient becomes insignificant. But you can show as the original author that their strategy doesn't perform better on all possible data. Finally, reanalysis strategies become difficult to reject if the ex-ante diagnostics perform better under their design than under the same model and same inquiry. So we have a set of R packages that help you to imagine your data before you collect it, to randomize and sample, and some fast estimators that make this diagnosis process easy. They're all up on GitHub, and we're going to be releasing them soon. We also have a set of web tools that make it easy to enter this software. So if you are not an advanced R user, this provides a kind of graphical interface for giving us the details of each of the steps of your design, and then a set of tools for inspecting the properties of the design. And we also have a set of Stata tools that we're working on that replicate much of the functionality of the R version. So it's all up on our website. This is funded by the Arnold Foundation and a great team of collaborators across the country. I think the main thing that I want to leave you with is that we've created a set of software tools to help do something that we all know we should be doing, but we want to, it's not really about the software tools. It's a recommendation for this 3-step process that we should all be doing before we carry out our designs, which is to declare them in terms of their model, inquiry, data strategy, and analysis strategy, to diagnose them, and then to improve them. So thanks. Our website is DeclareDesign.org, and yeah, that's all.
Any questions for Graeme?
That late afternoon slump. So.
Or it'll be available. It'll be available after, I'm sure. So, thanks again, Graeme. Oh, we have a question over here.
Very interesting talk. I have just a question for clarification. For instance, when you fix the sample size at 250, when you reach the statistical the power, it was, I think, 0.60. And then to get the 0.80, the sample size was 500, so double the first. So how do you account for the cost of the sample size? Because the sample size is a function of cost. So if I don't have enough money, I wish to have a sample size of 500.
Yeah.
I don't have money. How do we include the cost in your tools? Thanks.
Sure. So I think this provides a way of thinking about what the trade-offs are in the different dimensions of your research design. So it helps you understand what the trade-offs are in terms of the power, but also other diagnose that may be important to you. You may, for some research, it may be so important to answer the question that what you want is a design that provides you an unbiased answer, but one that's underpowered. This would help you to easily graph the trade-off between power and bias across sample sizes, and then you could see where you think that trade-off is, even if it's below the kind of traditional trade-off. So I think that's the main way that it can help, and it focuses attention on what that trade-off is to you. Yep. There's one more there.
Thanks, Ben Arnold, epidemiology at UC Berkeley. Really enjoyed this, and it looks like useful tools. I had 2 questions. One is, will the software accommodate other estimators? So, just is it flexible to accommodate any estimator? I'm asking specifically with an eye toward, we use semi-parametric estimation here a lot, and it'd be helpful for us in our study design and planning to easily be able to account for that. As opposed to assuming a model, for example.
Yeah, so I've kind of shown you the simplest way to use this, which is to use some of our built-in tools for common forms of random assignment and sampling, for using our data generation package that helps to think about hierarchical data in particular. That's often hard to generate in R. But none of it is dependent on those tools. And for any of these, if you want to use our sampling and assignment software, but not our estimators, then you just provide you write an R function that takes data and returns an estimate, and then that gets piped in. So for the population here, you can write your own population function, and then you just tell us this is the population function, and so you can enter and exit as much as you want.
Great. That's great. My second question related to your nomenclature of a good design, and it seemed like this was very much about a diagnosis of whether it's well powered. But I'm curious, taking a step back as an epidemiologist, whether there's any guidance toward just a radically wrong design. For example, we see sometimes people using, a cohort in evenly balanced, say, trial design with a super rare outcome. It makes absolutely no sense. Sampling should be based on the outcome itself if it's not a trial. Would this software give advice in that way? Like this big picture, it really relates a lot of times to the sampling design used to, is essentially a data generating function. I couldn't quite tell if that's going to be a feature of this as well, because that's often a big part when we're designing studies. It's a key question in terms of what's a reasonable or good design beyond power.
Yeah, I focused on power, I think, just because it's easy to wrap our minds around. That's what all the existing tools can essentially only estimate the power. We provide a set of built-in diagnosands that include power and bias and RMSE and coverage and the type S error rate and the exaggeration ratio. But our idea is that in different research communities, there are different answers to the question, what is a good research design? And it's really easy here to set up your diagnosand, which is the kind of answer to that question. So you just give us the function that says, please run my design over and over again, and now run this function that summarizes the design in any way that you want. And I think what we hope is that through our website and through GitHub, we'll be able to have people contribute back those diagnosands. So we have this huge range of different kinds of questions people might want to answer. So it's not going to give you direct advice about what to do. It's going to calculate the diagnosands for you. But I think the other way to answer that question is to say that the other part of this, we're developing a design library that's on our website. We have 3 or 4 of them right now. And we're going to be building that out ourselves and then seeking contributions of people who have written up a design from their domain and asking them to contribute back that code and a description of what the design does. And then we'll have a diagnosis and a Shiny app that lets you kind of explore their design. And so hopefully through that, there'll be a range of design advice that's sort of more domain specific.
Thank you. I just wanted to make sure I'd have a job in 5 years.
Thanks.
All right, thanks everybody.
All right. Thanks so much.